Welcome to the Walton Pi. Today we are going to be talking about the formal definition of a definite integral. We will not be going to the shortcut method of being able to compute them using an antiderivative. If you would like to see that, please check out my video on the fundamental theorem of calculus where I go into that in more detail. Here we are going to be talking about the limit definition involving summations. So let's suppose that f of x is defined on the closed interval from a to b, and then that interval a to b is divided into n subintervals, each of length b minus a over n. We are going to say that the length of the subintervals is delta x. So delta x is going to be defined as b minus a divided by n. If a equals x naught and then xn equals b and then x1 through xn minus 1 are all the endpoints of the intervals, so we break it up into n intervals, and then we just label the different endpoints of those in order from x0 through xn, and then we let t sub n be any point in our nth interval, going from x sub n minus 1 to x sub n, then the definite integral of f from a to b, so the integral from a to b of f of x dx is equal, or is defined to be equal, to the limit as n goes to infinity of the sum from k equals 1 to n of f of t sub k times delta x. So what this is saying is we are going to break this up into an infinite sum where we take delta x as the length of our subintervals, and then f of t sub k, that's the value of the function somewhere inside our interval. If that limit is defined and exists, then the definite integral from a to b of f of x is equal to that limit. So let's just state a theorem that helps us understand when they exist. So if f of x is continuous on a to b, or there's only a finite number of jump discontinuities, then f of x is integrable on a to b. So that means the definite integral from a to b of f of x dx exists anytime f of x is continuous on the interval. A simpler way to write the definite integral is to, rather than saying, I'm going to allow me to take any value inside my interval, let's just take the start endpoint. So we are just going to be taking, or I guess our ending endpoint, our nth, our rightmost endpoint of the interval. So we can write the definite integral, so the integral from a to b of f of x dx, we can write that just as easily as the limit as n goes to infinity of the sum from k equals 1 to n of f of x sub k times delta x, where delta x is b minus a over n, and x sub k is the right endpoint of the interval, or in other words, a plus k times delta x. So we've gone forward k of our intervals. This is another way that we can write the definite integral, and this is often an easier one to write down rather than saying, oh, I can pick any value inside the interval. If I'm always picking the right endpoint, it makes writing the sum much easier to do. In the process of doing these, you're going to need to start to know a lot of these different sums and what they're equal to. So some useful sums to know are the sum from k equals 1 to n of k. That's just going to be n times n plus 1 over 2. The sum from k equals 0 to infinity of k squared, well, that's just n times n plus 1 times 2n plus 1 over 6. The sum from k equals 0 to infinity of k cubed is n times n plus 1 over 2 all squared. The sum from k equals 1 to n of c is just c times n. The sum from k equals 1 to n of c times a sub k. We can pull the c outside of the summation, so that becomes c times the sum from k equals 1 to n of a sub k. And then if we are adding two things inside a summation, we can break that up into the sum of, the sum of sums. So the sum from k equals 1 to n of a sub k plus b sub k is the sum from k equals 1 to n of a sub k plus the sum from k equals 1 to n of b sub k, and then the same thing will apply if we are subtracting. If we're trying to approximate an integral with a sum, the midpoint is often a better approximation than using the endpoints when we are trying to use like f of some point in our interval times delta x. If you pick the midpoint of the interval, That often gives a better approximation, though it does not always. So the midpoint rule is just how we are choosing what point in our interval we are wanting the function to be represented by. So we can say that the integral from a to b of f of x is approximately the sum from k equals 1 to n of f of the midpoint of our interval times delta x. So delta x is still b minus a over n, and then x sub k is the midpoint of our kth interval, which is x sub k minus 1 plus x sub k all divided by 2. So we can approximate our integral using this midpoint rule. Some useful properties of the definite integral are the integral from a to b of f of x dx is negative integral from b to a of f of x dx. The integral from a to a of f of x is equal to 0, no matter what f is. And then the integral from a to b of a constant is the constant times b minus a. We can also break up integrals through summations. So the integral of f plus g is the integral of f plus the integral of g. The integral of a constant times f is equal to the constant times the integral of f. And then the integral from a to c of a function is equal to the integral from a to b plus the integral from b to c of that function. We also have some comparison theorems. So if f of x is always bigger than 0, then the integral from a to b of f of x is always greater than or equal to 0. If f is always bigger than g, then the integral of f is bigger than the integral of g. And if f of x is always between little m and big M, then the integral from a to b of f of x is always between little m times b minus a and big M times b minus a. I hope this video was helpful in understanding the concept of a definite integral. Please check out my next video where we will go through some examples, and please check out the video that comes after where we will go through the shortcut using the fundamental theorem of calculus to be able to compute these without always having to go through and calculate these sums. I hope you enjoyed it, and good luck with the rest of your math.